Here's an example for forced vibration of a damped system. It's basically problem 2.35 in your textbook. Given this massless rod, a mass is attached to its end and the force is applied at the mass. We have a spring, a damper, separated equally along the 1.5 meter long rod. The parameters given are that K is 2,400 newtons per meter. C is 30 Newton second per meter. Mass is 32 kilograms, and the force F of T is 50 times cosine frequency 2 pi T in newtons. Now we need to find the steady state response. Steady state response. Now, here before I proceed, I want you to notice something. Now, the total response of forced system includes a homogeneous or natural response and the forced response. The natural response we got for the damped systems was e to the power negative zeta omega n t times constant a cosine omega dt plus b sine omega dt plus the forced response, which was some amplitude x cosine omega t, forcing frequency, minus phase angle theta. Now, notice that the natural response, as time goes by, this term, the exponential term, goes to 0, and this natural response disappears, and the only term that remains is the forced response. And that's why another name for natural response is usually referred to as the transient response. Because it dies and disappears with time, and what remains is the forced response, and that's why the forced response is known as the steady state response. So, in this problem, I need to find the steady state part of the response, which means I'm looking for this forced response part. First, to proceed, I need to start by deriving the equation of motion of this system. Now, the degree of freedom in this system is basically the rotation of this rod with the mass attached to it around the fixed point here. So we'll assume a variable theta and derive the equation of motion in terms of theta. Now, I'll start with finding the kinetic energy term, T, and the only body I have is M, so it will be 1/2 mv squared, which is 1/2. Now, what is the velocity of this mass? This mass, it's a rotational velocity, so it's a tangent velocity v equals r omega or L theta dot. So it's m times L theta dot all squared. Now I can either substitute numbers now or leave it to the end, and after I finish all the derivation, substitute those numbers in the final equation of motion. I will proceed with the variables like this. So that's the kinetic energy part. Now the potential energy part is we only have a spring as a potential energy part in this problem. So it will be 1/2 K. Now what is the deflection in the spring? Okay. The length here is 0.5 meters, so it's r times theta. Of course, we're assuming small theta here, so it's the length of the arc, which is r times theta, and r in this case is 1/3 of the length of the beam. The beam is 1.5, so the 1.5 meters. So this will be L/3 times theta all squared. And finally, the Rayleigh's dissipation function is 1/2 C, again V squared. Let me call this the C to differentiate this from the velocity of the mass. Now, in this case, again, the velocity Vc is the radius times omega, and omega is theta dot. So the radius in this case is 2/3 of the length of the beam. So it's 2L/3 theta dot. So this is 1/2 C 2L/3 theta dot all squared. So I can further expand those terms. 1/2 m L squared theta dot squared. This is 1/18 K L squared theta squared, and this is 4/18, that's 2/9 C L squared theta dot squared. Now, here we have force applied to the system, so I will have to include also the work done by this force, and the work is the force F of t times the distance of the force. Force moves down, the length of the arc is L times theta. So this will be F of t times L times theta.